Good evening, class. Uh, Welcome to class third of the electronic theory of solids. And in today's this assignment number 3, I'll be discussing about the Fermi energy and the partition functions, different density of states, and basically the canonical pressures. All those things will be discussed in this class. Yeah. So having said that, I will start with, as usual, with a few of the numerical questions, uh, which will give you a better understanding of the concepts and how to evaluate if few of the given parameters are there in the question, and then if you have to determine the known parameters, then how you can approach the problem and what's the physics behind it. I'll be covering those things. So having said that, I'll start with the question number 1, which is like the number of the conduction, electrons per unit volume for silver is given. Let's say this number is roughly 5.86 into 10 power 28 per meter cube. Yeah, it should be per meter cube. Then the corresponding Fermi energy. And Fermi temperature are. Yeah. So we have to evaluate two things. One is the Fermi energy, and the other thing is the Fermi temperature. And the given parameter is the Carrier density, which is 5.86 into 10 power 28 per meter cube. Important thing to note is that in metals, this number is 10 to the power 28. So you have enough number of electrons per unit volume that can do the conduction in the system, and that's why the metals are good conductor. In the electrons, the number of these free electron is very less, and that's why they are not a good conductor of the electricity, these free electrons. So let me just write then. Number density given is 5.86 into 10 power 28 per meter cube. And the Fermi energy, we know the energy form, Fermi energy at wave vector kf is nothing but EF is equals to h bar square kf square by 2 times mass of electron, right? And if you follow the classroom notes, basically the lectures, we know, and this I will derive also in the subsequent part, the relation between wave vector kf and n follows kf is equals to 3 pi square times n to the power 1 by 3. You can see this dimensionally correct because 3 pi square don't have any dimension, and n number density has dimension of per meter cube. So if you take 1/3 of it, it will be inverse of the length, and that's essentially the dimension of the kf, which is length inverse. So if you substitute, this is equation number 1, this is equation number 2. So now if you substitute equation 2 in equation 1, then what you get is EF is equals to h bar square. Instead of kf square, it will be 3 pi square n to the power 2 by 3 divided by 2 times mass of electron. So now we know the value of these fundamental constants, we know that h bar is nothing but 1.05 into 10 power uh, minus 34, I think, joule second, and pi is nothing but 22 by 7. Number density is given, which is 5.86 into 10 power 28 per meter cube, and mass of electron is 9.1 into 10 power minus 31 kg. Yeah, so if we follow these numbers, what we get is like your EF will be h bar square, which will be 1.05. You can substitute these values, so it will be 1.05 into 10 power minus 34 to the square. 3 into 22 by 7 will be 3.14 roughly square times number density, which is 5.86 into 10 power 28 to the power 2 by 3 divided by mass of electron times 2. Yeah, 2 times mass of electron. Mass of electron is nothing but 9.1 10 power minus 31 kg. And let's now take the dimensions also. If you see, the dimension of this one will be in the form of joule, right? Because the others will cancel out. And in that case, your EF, if you do a bit of the mathematics to evaluate the numbers out of it, you will get the numbers to be 8.798 into 10 power minus 19 joule. So this is in joule, right? It's a very small number. That's why in the metals, this Fermi energy comes roughly 10 to the power minus 19 joule. And if you see, there is one more number which has this order of 10 power minus 19, and that's electron volt, right? So if you see value of the electron, it is 1.6 into 10 power minus 19 coulomb. So what you do in these cases, you multiply this number and divide this number with E. So 8.798 and 10 power minus 19 times E and divide by also E, right? And joule, basically. And in that case, it will be, if you do so and divide it by, replace E is equals to 1.6 in 10 power minus 19. So it will be around 8.798. Let me just calculate what this number will be. Around 8.798 divided by 1.6 is around 5.498 into, and then this E times joule is nothing but EV. So this is the Fermi energy, basically. And let me just maybe check the real number of the Fermi energy of uh, silver. Fermi energy of silver. What is the real number of silver? Whether these numbers are, yeah. So if you search on the internet, the search the articles on silver, and you will see that the actual number density, actual energy, Fermi energy in the silver is roughly 5.5 ev, which is essentially the same what we extracted. So that's the importance of knowing the just by knowing the number density. And in metals we know that electrons are almost free kind of thing, so that's why we take here m is equals to free electron mass. If they are bound kind of thing in semiconductor or those things, then we take the effective mass that would be given in the question. And so whatever we extracted just from the carrier density, the energy matches very precisely with the real number for the silver. This tells you that in metals the electrons are free, the effective mass is like the mass of the electron mostly to the order, and mm, the derivation of your, basically the from the Fermi Dirac distribution whatever you derive, the energy equations and all those things, and they hold, right, into the real world application. So your quantum mechanics works. That's what it means. Now, if that's okay, then let's move on to the next part, which will be the second part here is, so this we extracted Fermi energy. Now we'll have to extract the Fermi temperature. So how you do so? Like in any quantity, if you have to extract the temperature, so you just in those cases, what you do is you equate your energy equals to the thermal energy scales, which is kBT. So how you do is like EF is equals to kb times TF, right? And your EF, you already know what you extracted. Not in the EV, we'll use the joule one, because then that will be your TF will be EF by kb. Your EF is nothing but 8.798 into 10 power minus 19, and this is kb is nothing but 1.38 into 10 power minus 23. So this one has the dimension of joule and kb has the dimension of joule per Kelvin. This gives you TF is equals to roughly around 6.4 into 10 power 4 Kelvin. So your TF is roughly, if you see, it's 6400, right, Kelvin, 64,000 Kelvin, which is huge, which is large, right? And what this number tells you is like in the metals, basically, whatever phenomena you see, right, these Fermi energy, all those things, they are quantum mechanical phenomena, and they will, since you observe them at room temperature, right, 300 Kelvin, which is very less than compared to the Fermi temperature. So whatever you are seeing, those origins are basically the quantum mechanical phenomena at these temperatures, in correspondence to the Fermi energy, basically. So if you want to see the classical part of it, then you'll have to go more than this temperature, and you know that above this like 64,000 Kelvin, even at 200 degree, 2000 degree centigrade, even below that, the silver will melt. So you can't see the physics of those metals there. That's why the quantum mechanics is important to understand these concepts. So this is about the question number one. If anyone has doubt, they can ask the question. I'll be happy to address it. Okay. If no one has the question, then I will move on to the next part of the problem, which will be linked to the problem which we solved. And the problem which goes is the second problem, which will be based on the Fermi-Dirac distribution function, basically. So this is question number 2, which is if temperature T for silver is, let's say you heat your silver, whatever silver you have at your home also, let's say you somehow heat it to the 800 Kelvin. And then if I ask you, then find the energy at which the probability that a conduction electron state will be occupied is 90%. So at what energy, basically, your occupied state's probability will be 90%. So that's the question. So then find the energy at which the probability that a conduction electron state will be occupied is 90%. So let's start this one. Response. So we have seen in the class notes that about the Fermi-Dirac distribution function, which determines the probability of a conduction electron state at any energy E. Right? So let me write Fermi-Dirac distribution function. The probability that a conduction electron state at any energy E is essentially given as Fe is equals to 1 over 1 plus exponential of E minus EF, EF your Fermi energy, and KBT. So the point to note is that this is the probability of occupation. In case if the question asks you, like for the empty state or the unoccupation, then it will be 1 minus F basically, Fe. That will be the probability of being the states empty, right? Here in this expression, your E is the energy of the carrier. Here, what is the carrier? Electron, right? Kb is your Boltzmann constant. T is your temperature. In this case, you have been given 800 Kelvin. Always remember one thing, the temperature which you use is always in Kelvin, not in degree centigrade. If it is in the degree centigrade, add a number of 273.15 to convert it to the Kelvin, or if it is in the Fahrenheit, convert it to the Kelvin. So that's the important thing, that you always convert your temperature to Kelvin and don't use it in the degree centigrade because the temperatures are different. 0 degree centigrade is actually 273 Kelvin, right? So if I ask you to draw this one, in the last class also I showed you like how this distribution function will go as a function of the temperature. So I'll just draw it once again so that it becomes clear. So let's say you are drawing your distribution function Fe, which is your probability of occupation, right? And the maximum occupation probability can be 1 and the minimum probability can be 0, right? Probability can't be negative. So let me mark the scale. This will be 1 and this is 0. This is the what minimum and the maximum probability can be. Now we'll have to plot our curve in this one. So let's say and this is our EF Fermi energy. Let me mark the EF also. Let's take the case T equals to 0 Kelvin. Let's take the case T equal to 0 Kelvin first. Let me take it in. Okay, the black color is good. Okay, at T equal to 0 Kelvin, if you see this expression at T equal to 0 Kelvin, if your energy, okay, let me just write the states down so that it becomes clear. At T equal to 0 Kelvin, for there are two cases, right? For E less than EF and E greater than EF. Let's see these two cases, right? So if E is less than EF, here in this expression, what will happen? This term will be e to the power minus negative by kBt, and e to the power minus infinity is nothing but 0. So 1 by 1 will be 1. So your Fe is 1 till the point you reaches EF. So you'll start from here and your FE will be 1 till the point you reaches EF. Okay, this line is complete now. Till this point we know that FE is 1. Now for if E is greater than EF, then what will happen? This quantity which is there on the top, E minus EF, will be positive. And positive quantity divided by 0 temperature will be infinite. And then your function will be e to the power minus infinity. E to the power like minus infinity, and that will go to 0, right? And in that case, your EF will be 0 here. And the transition is in step kind of transition. This is for t equal to 0, black one. Now the second case comes when you have finite t. For finite t, and t not equal to 0 Kelvin, then in that case, for E very less than EF, this condition still hold. FE will be 1. And for E is equals to EF, what you will get will be 0 by finite number. E to the power 0 is 1. So 1 plus 2 is will be half. So FE will be half. And for E greater than EF, FE goes towards 0. Right? So now this tells you if you have finite t, when your t is not 0, then at this point, yes, you will be having 1. At very extreme, when E is very large than EF, yes, then 0. At E is equals to EF, you will be having value half, which somewhere here half will come. And the transition between them happens like this. So this is for T not equal, T greater than 0 Kelvin. Right? And in our case, we have T equal to 800 Kelvin. So we fall in the category of second case. And what the question is asking is, like, the question sharply asks that, okay, at what energy the probability that a conduction electron states will be occupied is 90%. 90% is nothing but 0.9, right? Somewhere here will be 0.9. So it is asking, okay, at this point, where the probability is 90%, what is the value of the energy? So this energy, E, the question wants us to estimate that what is this energy at this point. What is the question? What is the energy at this point? Basically, this is what the question is asking. It's E. And how do we determine that thing? So we will compute our FE to be 0.9. Our EF is already we estimated from the last question, right? And our temperature is given. Boltzmann constant we know. We just have to play with the equation and extract the values. So let's just use the values which we have. So FE given in the question is 0.9, and that will be equals to 1 over 1 plus exponential E minus EF by kBT, right? And if you just manipulate the equation, so it will be 0.9 plus 0.9 times exponential of E minus EF by kBT is equals to 1, right? And that will give you 9 exponential E minus EF by kBT is equals to 1 by 9, right? Now, whenever you have to solve these equation and you have to estimate the E, in those cases, always take log. So if you taking ln both side, so there are two type of log. One is ln base E and another is ln base 10, right? So if you take ln base e, the exponent, the part which is there on the exponent, which will come down. So if you take ln exponential of e minus ef by kbt, this will be essentially e minus ef by kbt is equals to ln 1 by 9, right? ln 1 by 9, you can estimate, this is just numerical number, and ef, which we estimated in the last question, was 5.5 ev, right? And the kbt, kb, which we know is Boltzmann constant, so kbt will be nothing but 1.38 into 10 power minus 23 times temperature is 800 Kelvin, and you have to convert it to the electron volt also. So divide it by 1.6 10 power minus 19. So what you get is around 690 into 10 power minus 4. So this will be a kbt. Substitute this A and B in equation number, let me call this one the equation number X. Substituting A, B in X. So what you get is energy E is equals to EF minus 0.151. This is the value of ln 1 by 9 times EV. ln 1 by 9 times this number, kbt will be 0.151, and E will be roughly, so EF you substitute to be 5.5 minus 0.151 EV, and that will be roughly around 5.348 electron volts. So when you are at this energy, okay, something, yeah, when you are at this energy, Fermi energy, your 90% of the states will be occupied. Okay, the another question can come, okay, at what energy basically your probability of occupation is half if I ask you at finite temperature? Then the straightforward answer to it is at the Fermi energy at finite temperature. That's what it is, right? When E is equals to EF, your probability of occupation is half. And this is the very standard result, that when you are at a finite temperature and when you are sitting sharply at your Fermi energy, your probability of occupation at that point will be half. Yeah. So this is the question. If anyone has any doubt or something, they can ask. I'll be happy to address the question or concern. And it's very important that you ask the question, because that will make sure that you understand the concepts well, and then you'll be able to impart this knowledge in your maybe assignment or in your exam in the NPTEL. Yeah. So then seems like anyone has any doubt or question. If that's the case, then I will move on to the next problem. I'll encourage you to write your question in the comment section. If you have anything in the chat, I'll address those ones. Yeah. So if there is no question, I will start the third problem, and there I will derive the relation between the kf, basically the Fermi wave vector, and the K density also, which I told you guys in the very beginning, that I will derive the relation which is kf is equals to 3 pi square n to the power 1 by 3. That relation also I'll show you like how it's been derived. So starting with the question, which is like, consider n electrons in a volume V with energy given as E is equals to 2 times summation of your wave vector k less than kf up to the Fermi wave vector. Basically, your states are there, and h bar square k square by 2m. Can any one of you tell me like what is this 2? Generally, what is this 2 factor? Where from where this factor of 2 is coming? the energy per electron epsilon and pressure P. Anyone who is willing to tell that from where this factor of 2 is coming in the energy expression? Yeah, right. So this is generally the degeneracy of the electron. So in normal metals, basically, you know that the spin part has degeneracy of 2. So that's why the factor of 2 is coming. And generally, you solve your questions in the terms of the degeneracy of 2. But it's not always the case. That's something which you should always focus on. If a large enough magnetic field is applied, then your Zeeman splitting will be there, and that will break your degeneracy. There, your degeneracy go to 1, right? Then your energy expression will change, and your relation between Kf and N will also change. Along with that, there is one more thing which you should focus, which is like for different materials, like which has like sublattice symmetries, like that case of the graphene, right? It has 2 spin and 2 valley degeneracy. So instead of 2, the factor of 4 will come. So you should always first see which system you are working with, and then account the degeneracy for that. Bye. Yeah. So this is so now the question is, consider an electrons in a volume V. Basically, they're confined in any volume V, and their energy is basically h bar square k square by 2m. That tells you that, like the free electron model, basically where you don't account the potential energy, you only care about the kinetic part, or the potential energy is absorbed in the effective mass. Then the energy per electron, which is epsilon, right? And the pressure exerted by these electrons, right? So there will be a positive pressure out of it. And so we have to estimate this positive pressure as well as the energy per electron. So for doing so, first we'll have to derive a relation between our Fermi wave vector Kf and carrier density N. To give you a picture of like what is this Fermi wave vector and the carrier density N mean, okay, let's say you are when you draw this dispersion relation, I don't know how many of you know it or not. I'm just for the everyone's clarity, I will draw this part. And in the quantum mechanics, you have discrete allowed states k, right? And then this axis is your energy essentially, and this is your k. K. Now, when you are sitting at this point, let's say this point, so it will be in 3D, right? So it will be something like this. So this will be your kf. Let's say this is your, or this is your k. Let's say this is your wave vector k. At this point, your energy is there, right? And the energy you will write E as a function of k. But along with the energy also, there is one more thing which you uh, in the term of which you can write this solution, which is the number density. For example, either you can count the energy, this y-axis scale, which is moving upside, or you can count the number of the electrons per unit volume, basically, which are occupied, and that is essentially n, your number density, right? And this relation between this number density and the wave vector k, I'll be deriving. So let me start with the total number of allowed states in 3D. Total number of allowed states, let me write very general expression in a dimension d. If your dimension is d, let's say 1, 2, 3, I'll write general expression. So your n, total number of the particles which will be there, will be g. G will be your degeneracy. Hmm? Generally, G is equals to 2 for metals normal, and G is equals to 4 for system like graphene. Times integral over d to the power dimension is Okay, I'll write the dimension, maybe dimension to be the x. So d to the power x integ okay, the phase space basically, then d to the power x, the real space, divided by 2 to 2 pi to the power x. So this is your general expression for dimension d. For dimension x, let's say if your 1D system is there, then x you replace with 1. If for 1D, your x is 1. For 2D, your x is 2. Your for 3D, your x is 3. Right? And general expression you can derive for like non-realistic spaces also, which we don't see in real life, which is like 4 dimension, 5 dimension. The relation you can still derive, like how the expression will be. So since in our case it is 3D, right? So we'll go with, and g is also given in our expression, which is 2 spin degenerate, as you guys only told me that it's a spin degeneracy, so I'll count it as a spin degeneracy. And then integral over d3k and d3l by 2 pi to the power cube. Okay, d3l, which is like the real space volume, is not, you can take it out of the integral, which will be 2 times volume, which is already given in the question. And then you are left with d3k, and then this 2 pi cube also you can take out. Now you need to do this integral d3k. The one thing is, which you can say that okay, we know that if I assume the system to be spherical, I can write its volume, which is essentially d3k, as 4 by 3 pi k cube, right? That's the volume of a sphere, 4 by 3 pi r cube. So similarly, or you can derive it also. Let's say you can assume your basically what you call, I mean, I'm forgetting the name. Um, you you treat it as a like a disk basically. You treat it like a disk, and then basically an area element associated with it, and then you integrate that area element, and from there you get the d3k to be 4 by 3 pi r cube. So let me just write 2 times v and 4 by 3 pi k cube, right? Let me just rearrange it, and what you will get out of here is k is equals to 3 pi square over 4 and 2 is 8, 2 to the power cube is also 8, so 3 pi square n by v to the power 1 by 3. So here k is nothing but 3 pi square times number density to the power 1 by 3. This is what your k will be, Fermi wave vector. And so now you have the relation between the Fermi wave vector and this one. Okay, now the question which is asked in the problem is the energy per electron. So the energy, see, I'm going in details of these derivations because I want, uh, yeah, so I mean, you're right. So it should be integral from 0 to kf. You're right. So you don't integrate it to the full space because after that the states are not even there. So this is all only like on a very rough scale. Ideally, what should you do is you multiply this one with your Fe, Fermi-Dirac distribution function, right? Fe, and then you take the states to be 0 to infinite. And now for your Fe, for k less than kf will be 1, and your Fe for k greater than kf Fermi wave vector will be 0, and that boils down your integral to 0 to kf basically. Only states which survives are these. When fk is equals to 0, in that case the value of the integral will be 0. So your 0 to kf, and your kf is Fermi wave vector, which will be 3 pi square into the power 1 by 3. Yes, you are right, it's just kf. Yeah, I just forgot to add the subscript. So the energy per electron So how do you write it is like you take your average energy and then you divide it by the total number of the electrons, right? That will be your average energy per electron. So energy expression is already given, which you have is like 2 times h bar square k square by 2m. So you take it like 2 by n and then h bar summation over h bar square k square by 2n, and your k goes from 0 to k is equals to kf, right? Yeah, that's the range of your k. Now you can this summation basically which is there, you can make it to the volume integral also, and to do so you what you do is like e by n is equals to 2 by n, and then you multiply it with the volume and the phase space. You multiply it with the phase space element 0 to kf, and h bar square k square by 2n times, again this kf, why it goes to only kf, again this logic comes from this Fermi-Dirac distribution functions, because after kf or after energy this value of the fe is 0, and whatever you multiply with 0 will be 0. So only states which matters are below ef. Again this assumption only work if your temperature you are treating to be 0 Kelvin. If you treat it to be the finite temperature, then you will have to multiply it with the Fermi-Dirac distribution function and then get the estimate the results. But for the temperatures which are generally there on for the metals, the results are essentially same. So D3K. So if I just solve this one, so D3K I can write to be the 4 pi k square and times dk. So h by square v by m 2 pi cube times 0 to kf k square 4 pi k square dk, right? So h bar square v by m 2 pi cube to 4 pi, and then k to the power 4 we will take to the k to the power 5 by 5. Can anyone of you tell me like how does this define this integral 4 pi k square dk? Where does this 4 pi k square dk come from? Anyone? Is there anyone who will explain this, where this 4 pi k square dk comes from? Okay, Mansi is saying that volume of Fermi sphere is defined in such a way. Okay, but I mean, um, that's what I'm asking. Like, why it is defined like this? Why not something else? How will you justify this one, this argument? So this is nothing but EF, your Fermi energy, times your Fermi energy EF, times your KF cube. And if you just substitute the values of the KF cube from equation, uh, let me call this equation as 1. Substituting values from equation 1 of KF, substituting KF equation, KF from equation 1. So what you get is like E is equals to V by 5 pi square n times KEF times 3 pi square n by V. So n cancel, V cancel, pi square cancel. So this is the standard results that average energy per particle in the system, this is n by E, is nothing but 3 by 5 times of your Fermi energy. This is the average energy of the electrons in the system. Okay, now the question which I asked was like, how do we write this as 4 pi k square dk? I will address this one. So the volume element of a sphere in 3D. So whenever we derive such things, we break our the larger picture into infinitesimal small. If it's volume, you break into the infinitesimal small area. If it is just area, then you break into the line. That's how, because from the line, if you add multiple lines inside of it, if there is a one line, right, this is 1D. But if you add one, two nearby, many lines, then they are very nearly, like, this delta x is very small, right? Small of the length scale. Let's say this is your length L. Then this will give you an area, right? Similarly, if you build along this area multiple areas on top of each other, like you have this area, then you have this one area, you have this area, you have this area, and when you combine them, you will get a volume, right? 3D. So this is 3D. So, and this is 1D, this is 2D, and then you go on 3D. That's how the things goes, right? So in the case of a sphere, if you are assuming your dispersion to be isotropic, which is like in all the three directions possible, x, y, and z direction, Cartesian coordinates, your system is isotropic, right? Then the isotropy is well preserved in cubes, in spheres, not in the cubes, because the cube are not isotropic, right? They have directionality, but the sphere don't have directionality. Spheres are isotropic. The cubes are anisotropic. So for cubes, for spheres basically, spheres, what you have is like, you can treat it as a the sphere which has area. We know the area is 4 pi r square, right? The surface area. If it has a radius r, its surface area is 4 pi r square. This also you can derive, this 4 pi r square also, basically by taking the this spherical coordinate system, and then you determine the area. This will turn out to be 4 pi r square. Okay, I'm not going into that right now, but now if you want to estimate the volume out of it, what you do is like, you think it as like, this is your one volume, one area 4 pi r square, and on top of that also you starts growing another surface which is infinitesimally thin, right? Maybe let me just bring this one side slightly. Okay, yeah. So this is like this, and this part is very small. Yeah. So I'm this is radius r, and this is dr, and your dr is very less than compared to r. In that case, if I ask you what is the volume element, this one, you will say this is 4 pi r square times dr, right? And now you want, if you want to estimate a volume of a sphere of radius, let's say capital K, what you do is 0 to capital K, and that will give you, if you integrate r square with respect to dr, you will get r cube by 3. If you substitute these values, what you will get is 4 by 3 pi k cube, and that's what we used here, this relation 4 pi k square dk. That's the reason behind using these basically infinitesimal small components, and then scaling your problem from 2D to 3D. These things are emphasizing because then if your basically concepts are clear, then you won't be afraid of any question. You don't have to remember any values. You can derive it within a minute. I mean, the things, and your concepts of for the future will also be protected. I mean, you don't have to memorize the things. Okay, if this question is clear, then shall I move on to the next part, which is like now the exerted pressure, how we determine the exerted pressure. Okay, so the question Next part is determining the exerted pressure. Yeah. So we know that pressure is nothing but from the thermodynamics del E by del V, and at a constant number density if your particles are conserved, right? And since we know that our expectation value of the energy per particle is nothing but 3 by 5 times number of the particles times the Fermi energy EF, right? And your carrier density small n you can write as n by V. Your Fermi energy you know is h bar square kf square by 2m, right? So the kf anyway you estimated earlier also. So now if I substitute the value of this kf, which is I estimated in equation 1, so let me just then estimate E by substituting the values 3 by 5 times n times h bar square kf square. Instead of kf square I put 3 pi square n to the power 2 by 3 by 2m. Here I substituted the value of the kf, and if I solve this expression basically, and I take that basically I write it like as 3 by 5 times n times h bar square times 3 pi square to the power 2 by 3 by 2m times n and v to the power 2 by 3 minus 2 by 3. I can write, right? And I substitute here, I substituted to be n by v. If that's the case, in that case, if I take the differentiation of it, that's what the pressure will be, right? Del E by del V. And if I do so, and if I just compute it, what I will get to be minus 2 by 5 times n by V times h bar square. You can solve this expression, n by V to the power 2 by 3 by 2m, and this is nothing but, you know, this is EF. So the pressure, which is like nothing but minus del E by del V, will be 2 by 5 times n by V is small n carrier density times the Fermi energy. So this is the standard results, that the pressure exerted by the electrons basically, you call it the degeneracy pressure basically, will be 2 by 5 times the carrier density times the Fermi energy. So that's what the relation is. And now further, if you want to write it in terms of the average energy, you substitute the Fermi energy with respect to the average energy, and then at that point you will get your pressure to be 2 by 3 times average energy by volume. So that's a different case. I mean, you can also write it in the different form also. So is there anyone who has uh, like any doubt or question about this degeneracy pressure and the concept which we discussed here about the Fermi energy and the average energy of the carriers in the system? Okay, if then there is no question, I will move on to the next part. I think this will be the second last to the last problem for the today's session. If anyone has any doubt regarding the class notes or anything else about any concept, they are welcome to ask the question in the chat. So the next question is the Fermi energy of a metal is 5.51 eV. The average energy of the electron is 0 Kelvin, is electron at 0 Kelvin is expressed as this one. So the temperature, the question which is like the temperature at which a classical free particle will have uh, energy, basically expectation value of energy E as a function of temperature, the temperature at which a classical free particle will have this much energy is given by T. Then determine both E and T. So you have to determine the average energy per unit, basically the particle number and the temperature, corresponding temperature. So it's an easy problem. You already derived the relation from here. You can use this relation, average number of the particles, average energy basically is 3 by 5 times the Fermi energy. So Fermi energy is already given. So all you have to do is 3 by 5 times the Fermi energy. And if you substitute the value 3 by 5 times 5.51 EV, what you get will be 3.306 EV. So this will be your response to that one. And the another part it is asking is, if there is a classical particle, at what temperature should I take the particle to such that its energy becomes equal to this average energy. So we know that in 3D, the classical part, the kinetic part of the temperature is kBT by 2. If it is in the 3 dimension, you multiply it with the dimensionality and it becomes 3 by 2 times kBT. So what you do is like 3 by 2 times kBT is equals to this 3.306 times 1.6 into 10 power minus 19 joule. And the kBT, you basically kB is the Boltzmann constant. You write the value of the Boltzmann constant, and the temperature which you extract is roughly 2.5 into 10 power 4 Kelvin. It's enormously large temperature. Right. So this much high temperature is required for the electrons to attain that Fermi energy, basically. Do anyone has any question about it? Like, is there any question on it? Okay, so and today I will just close the session at this point because I'm really sorry I got an urgent work. I have to finish that. In the next session, I will take a few of the problems from this section also, and along with that, the next assignment. So the problem which I will be taking in the next assignment will be based on the Hall coefficient experiment, and then the forward part of it, and the Cronin Penning model, all those things I will also discuss about. And till the point regarding this Fermi energy, regeneracy pressure, and different dimensions, basically. If you have any question, you can ask. If there is no question, you guys can leave the meeting. It's totally fine.